Hello, everyone, and welcome back to the Fundamental Theorem. Now, it might be a little surprising that I'm posting on a fairly random topic. Why do hyperbolas have asymptotes? As opposed to maybe continuing some of my existing series, such as the logic one and the one on trigonometry. But I'm afraid that I haven't had much time to make videos, and I'm afraid I still won't have enough time to make elaborate videos such as those. I'll try and post them as often as I can, but I make no promises. So instead, what I thought I could do is rather than tune myself out completely, I can post what I'm going to call quickies. So short, maybe 5 to 10 minute videos on random topics, something from here, something from there, and just really put them all together. And just I'm just going to do them using the markup tool on Apple Notes. So nothing very fancy. I'm not going to make those elaborate presentations and animations and all that. But I think this should work. Right, so to the question at hand, why do hyperbolas have asymptotes? Well, okay, for those of you who aren't familiar with what a hyperbola is a sort of conic section. So a conic section is essentially whenever I have a cone, right, I can sort of take a section of it's quite literally a conic section. So if I have a cone that looks something like this, then I would have a two halves of it, and then if I took a section along something like this, that would give me hyperbolas. Okay, so that's pretty much what it looks like. But yeah, so a hyperbola generally has an equation that looks like this, and you could have two orientations of hyperbolas. I'm just going to go ahead with this one. So you say generally this is the sort of most basic form of a hyperbola. So y squared minus x squared is equal to 1. You could also have x squared minus y squared is equal to 1. And in that case, the orientation will be flipped. But let me just go ahead and sketch this on a pair of axes. So if yeah, that's my y and my x. So a hyperbola of this sort would look something like that. And I would have another half on the bottom. And these hyperbolas have asymptotes. So that's not a very good asymptote. It's a very vague, it's a very rough sketch of an asymptote. But yeah, these are the two asymptotes. This one has equation y equals x. And this one right here, the other asymptote that really shouldn't be touching the graph, but that kind of is because my drawing is terrible. This one has equation y equals negative x, right? So why does a hyperbola have these asymptotes? What explains this behavior? Well, there's a geometric approach and there's an analytic approach. And I'm going to go ahead and give the geometric approach because it's very simple. It requires no knowledge of things like calculus and stuff. And those who are interested, I'm just going to include the analytic one as well. Okay, so let's go ahead with the geometric approach. Now, okay, so let me just rearrange the equation first. Y squared minus x squared is equal to 1, which is equivalent to saying y squared is equal to x squared plus 1. And already, I'm just going to rewrite this 1 as a 1 squared. And already this seems to have a very familiar form. For those of you who know the Pythagorean theorem, you would immediately recognize this. So essentially what I would have is I can draw a sort of right triangle. I didn't know that Apple Notes did that. But yeah, I can draw a right triangle. So let me just call this angle theta, and I'm going to go ahead and call this angle phi for no particular reason. So then this guy, let's say this has length 1. If this side has length x, then this side has length y by the Pythagorean theorem. That's pretty much what this general equation is saying. That's the same as this, right? So my input or my independent variable is the length of this side, and my dependent variable is the length of the hypotenuse. So let's say I increase x, and let's say x is approaching infinity. All right, in other words, x gets arbitrarily large. What do we observe then? Well, first of all, we know that we let's just write this. So tan of theta is going to be what? 1 over x, right? And we know that as x approaches infinity, tan theta will approach 1 over, well, you can't really say 1 over infinity, but pretty much, yeah. So it approaches 0. So maybe you can think about this as 1 over maybe 10 is 0.1, 1 over 100 is 0.01, 1 over 1,000 is 0.001, and so on. So it becomes closer and closer to 0. Yeah. So then, if tangent of theta is like nearer to 0, and remember we're given that 0 less than equal to theta less than equal to 90 degrees. Right? So theta is an acute angle. I don't know if you would strictly say less than or equal to, but let's just go with it. So you have this, right? So that means that theta would also be 0 because tan of 0 is 0. You see? So for tan of theta to be 0, theta would be 0. So we take theta equals 0, or well, the real way to represent this is theta tends to 0, but let's just go with it. Yeah, then we would get phi is equal to 90 degrees minus theta, which is 90 degrees, right? So again, it's not exactly equal, but let's say it's tending to it. So if phi is 90 degrees, then imagine what this figure would look like. This figure would look like this. You have a vertical line, you have a horizontal line, and you have another horizontal line, right? So you have that these two guys are actually parallel to each other, right? Because this angle is 90 and this angle is also 90. So these should meet over here. That's the extent of how terrible my drawing skills are. But okay, now we also know that if they're parallel, they never converge. But we know that they do meet at some point. They sort of they meet at a point, and that point is this point right here. We know that for a fact, right? So if they meet at a point, but they're also parallel, then the conclusion is that they are pretty much the same line. Now, if they are the same line, then they would not have any distance between them. But that's really that's really what happens when you consider things that are tending to infinity, and when you have all of this weirdness because finite values like one. Are we saying that one equals zero? No, by no means are we saying that one equals zero. What we're instead saying is that it can kind of sort of be visualized as being the same. It's not going to be the same, and we definitely will never reach a case where theta is truly zero. But that's why we're considering theta tending to zero. That's why we use the word tending to sort of escape all of this weirdness. So yeah, I think that pretty much clears that up. So I'm just gonna get rid of this right here. And yeah, so then what have we established? Well, if this guy is y, right? I cannot draw curly brackets. Well, I guess I can. Okay, but if this guy is y and this guy is x, and we have y and x in the same line, then the length would approximately be y equals x. You see? And that explains why this graph tends to the line y equals x. You see why it kind of sort of approaches this line, gets closer and closer to this line, but it never quite achieves this condition. And the reason for that is precisely because this is still a finite length, and we can't just ignore it, but we kind of are. So, weirdness with infinity, I mean, you know how it works. So I hope that kind of explains the intuition for why a hyperbola has an asymptote. And really, if you want to look at the other orientation of hyperbola, that would look something like this: x squared minus y squared equals 1. And that would look kind of like this. So the exact same figure, and just make that a little more accurate. But yeah, it's pretty much the same thing. But yeah, you can just do the same argument, replace this guy with an x and replace this guy with a y. So it just works itself out right there. But I did promise a more sort of viable justification for this. And okay, so if we had to say, now let's go back to the original equation: y squared equals x squared plus 1. Take y equals the square root of x squared plus 1. That's an equal to sign right there. So just take this. And if we want to say if we, okay, let's just put a plus minus there. If we want to say that square root of x squared plus 1 plus or minus equals x, right? And in fact, it's plus or minus x because you have two asymptotes over there. And really, you can deal with that over here as well because you're squaring everything. The square root gets rid of the negative. But yeah, it's pretty much the same thing. So if we want to say something like this, we just square both sides. Okay, let's just go ahead and do that. This looks very messy, but then we get x squared plus 1 equals x squared. Now, this is never true because this is like saying that 1 equals 0, essentially the same paradox of sorts that we get over here. But that's the whole point. We're not looking at the graphs themselves. We're looking at something known as asymptotic behavior. So it's more of like a sort of weird where you overlook the weirdness, if that makes sense. So then what we're really considering is the limit as x tends to infinity of this thing x squared plus 1 over x squared. Because if this guy is equal to 1, right, if this limit evaluates to 1, that's like saying that this is true because then, I mean, because this is nothing but x squared plus 1 over x squared is equal to 1. You see, so it kind of works itself out. And over here, you can use L'Hopital's rule because both functions are very nice, continuous, differentiable, all of that. So you can just go ahead and say limit as x approaches infinity of 2x over 2x, which is obviously just 1 because these just cancel out. So, I mean, you aren't really going to sub in x tends to infinity. And if you really want to go a step further, you can again differentiate this and you get limit as x tends to infinity of 2 over 2. So that's definitely just going to be 1. Yeah. So that's pretty much the analytic justification for why a hyperbola has a limit. And yeah, that's pretty much it. I hope I haven't taken too long here. I might have, but I mean, this might not be a very quickie, so to speak. But yeah, this is the general format in which I would like to have more of these quickies. Just going to be videos that I record, and I'm just going to use Apple Notes on my iPad. Just write it all down over here. And yeah, that's pretty much it. All right, so thanks for watching the Fundamental Theorem, and do subscribe for more quickies and for more detailed, lengthy videos. And I'll try and post something on probably implication as and when I get time to as part of the logic series. All right, so hope you enjoyed the video, hope you learned something, and yeah,